Okay, for this lesson we're going to look at what we call similarity. Now I'm going to begin with a couple of triangles. Let's say that I have this nice triangle here. It's going to be 3 centimeters by 4 centimeters and a right angled triangle, and it looks like this. So this is 3 centimeters, this is 4 centimeters. Now because I know Pythagoras, I know that this other side is 5 centimeters. Okay, we can worry about the details of that some other time. Okay, you guys already know Pythagoras. Now, let's say that we make this triangle bigger. Okay, I'm going to draw another triangle over here, and it's going to be the same. It's going to also have a right angle in it. Okay, so it's going to look quite the same, but it's just going to be a bigger version. All right, so what we're going to do first is make this side twice as long as in the first triangle, and we're also going to make the other side twice as long. So we're going to have 4, 8 across here. Okay, and let's join it. So here we have 6 centimeters, here we have 8 centimeters, and we know therefore that this one is 10 centimeters. So you can see that there is a relationship between the side lengths of these triangles. They are the side length of the bigger triangle are twice as big as the side length of the smaller triangle. This can be shown in a ratio table. Okay, we've been working with ratio tables so far. We can also put this into a ratio table. All right, so let's have a look. In our ratio table, we have side AB, we have side BC, and we have side AC. Okay, and in the bottom part of our ratio table, I made that terribly crooked. Okay, in the bottom part of our ratio table, the equivalent of side AB is side DE. Okay, those are the same sides. BC is the same as EF, the one that goes along the bottom, and AC is the same as DF. Okay, and if we fill in these sides, AB was 3, BC was 4, and AC was 5. All right, and in our bigger triangle, DE was 6, EF was 8, and DF was 10. Now, if we look at the cross multiplication, you will see that we get the same result each time. Okay, so 4 times 10 is 40, is equal to 5 times 8 is 40. Okay, so that ratio holds. Let's do it here. 3 times 8 is 24. And that's equal to 6 times 4, which is 24. Okay, so again it holds. So this ratio table shows us that there is a constant relationship between the sides of the triangle. Okay, now hopefully you can also see something else about this triangle, or these triangles, sorry. What you can see is that right angle hasn't changed, has it? It's the same. Okay, you should be able to also see that this angle at the top here in triangle ABC still looks pretty much the same as this angle at the top here, and actually they are the same. All right, and this lovely angle over here is also the same as this angle here. Okay, so when we enlarge a triangle, we don't actually change the angles. All we do is change the sides by the same factor. Okay, now this is what we call similar triangles. So these triangles are similar triangles. Okay, and when we want to use we can use this property in order to find missing sides and missing lengths. Okay, so for example, if we didn't know what DE was, we could use this ratio table in order to do that. Now, there are some important things about this. Before you use a ratio table, you must always prove that the triangles are similar. So before using a ratio table, we must first prove that the triangles are similar. Oops, that's not how you spell triangles. Are similar. Okay, and over the next few lessons we're going to look at how to do that. Okay, so in this case we would have done the whole proof. You go through the steps. We're going to look at proofs later on. Okay, and then at the end we have to write down this proof. Okay, so we would finish this off with triangle ABC, and this funny symbol here means is similar to. So is similar to, and then triangle DEF. And you'll notice I made sure that I wrote the letters in the same order. So A was the equivalent of D in the first corner. Okay, so corner A and corner D, or vertex A and vertex D were the same, so they're in the first position. Vertex B and vertex E were the equivalent, they were the same measurement, so they are in the second position, and vertex C and vertex F are in the third position. And that's really important when you do similarity as well, that you get this order correct. Okay, now when we do similar triangles, as I said, firstly we need to prove that we have similarity. Now for your first lot of exercises, that's going to be pretty simple. We're not really going to do a proper proof. You're just going to write that they're similar, okay? But then you can start using a ratio table in order to do this. It doesn't really get too much harder than what we have here, okay? So let's just do one quick example. Let's say we've already got triangle ABC. Okay, this is a different ABC to the previous one. And let's say we have triangle, let's make it a different orientation. We'll say that this is triangle KLM. All right, and we're going to mark it. So we're going to say that we know that this angle and this angle are the same, and this angle and this angle are the same. So as I said, later on you're going to do proofs with these. We're going to show this correctly. But firstly, in this case, we're just going to look at the similarity part, okay? So triangle ABC is similar to triangle, and we need to use that same reference. So A was the right angle. In our second triangle, L is the right angle. So we're going to start with L. We don't do this just alphabetically. B was the blue one. So M is the blue in the second triangle, and C was orange. And that means K is orange in the second triangle. So we've just proven that these are similar. If I say that this is again a 3, 4, 5 triangle, and let's say that KL is, I don't know, let's make it 7 centimeters. Okay, or just 7 units, it doesn't really matter what they are. And let's say we want to find ML. Okay, we can put this into a ratio table. So we've done our proof. Let's pretend we did it. Make our ratio table. Okay, and here's the bit that people find difficult. Firstly, label your one triangle in the ratio table. Then you need to find those equivalent sides. So AB was the square root side to the square root side of the 90-degree side, 90-degree vertex to the blue. Okay, so 90 degrees to blue is LM in the second one. Okay, BC is blue to orange, which is M to K in the second one, and AC is 90 degrees to orange, and that's LK. Okay, so you guys have to make sure you get this right, and it's one of the hardest parts to do here. All right, now we fill in what we know. So we know that AB was 3. Okay, we know that BC is 5. We know that AC is 4. In our second triangle, we know that KL is 7. So that's our third one here. And we want to find ML, that is X. Okay, in this case, BC, MK, not important. We don't care about them. That can go away. All right, but it's always good to get in that habit of filling in everything you know, because you might need it for later. Now we just do the usual cross multiplication in order to calculate LK. So we have here AB times LK is equal to LM times AC. Okay, so AB times LK means 3 times 7 is equal to 4x. 3 times 7, you guys all know, is 21, is equal to 4x. Then we just need to divide by 4, and we will get x is equal to 21 over 4. We can leave it at that, or we can change this. In this case, 21 divided by 4 gives us 5 1/4, and I think that that's pretty nice for this one. Okay, please don't turn them into decimals. Okay, decimals, we don't know if they're accurate or not. Okay, they might be accurate. It might say, well, in this case it would be 5.25, but we don't know if you rounded that. Okay, so you need to keep things as fractions as much as possible. So this is how we work with similarity. Okay, we will do this in far more detail over the next few lessons. The big thing to remember is that similar triangles are just an enlargement. So similar triangles are an enlargement of another triangle okay. The sides are enlarged by the same ratio. And the angles are congruent. Okay, congruent just means the same. All right. Usually, at least in Australia, we would teach congruency and similarity. You guys only have to learn similarity, which makes it a little bit easier for you. But basically, congruent just means that these angles are the same. Okay, they're equal to each other. So with similar triangles, one of them is just an enlargement of the other. They're enlarged by the same ratio, so that means we can use a ratio table, and the angles stay the same. They are congruent, and we are going to use that property of angles being congruent in order to prove similarity in later lessons. Okay, the first lesson is very, very easy, but we'll go straight into actually proving similarity, so you'll need to go straight to the next video, because I think that this was this section is not super useful. There's only 3 questions in the book about it, and they're very easy. Okay, good luck.